So let us start. Today I will be talking about replica symmetry breaking. First lecture will be about Parisi scheme of replica symmetry breaking for infinite range spin glasses. But we will start from the simplest version of one-step replica symmetry breaking, and then come to the full scheme developed by Parisi. Next lecture today will be about other types of spin glasses where this simplest one-step replica symmetry breaking will be sufficient. So we start from the same point as week ago. We consider average partition function in power n. We used saddle point approximation based on large n limit. So these equations you already have seen. The point is how we will parameterize matrix Q alpha beta. Previously, we just assumed that all of diagonal elements are equal, which was found to be not sufficient, since it was leading to some unphysical results. Now, next step. Next step is demonstrated on this slide. Again, there is a zero on diagonal because this diagonal is trivial, just equal to 1. But here, instead of making all of diagonal components of a matrix equal, we make simplest generalization, namely, we choose some blocks of size m close to near diagonal to have order parameter q1. And outside this block diagonal, it will be some q0. This is, of course, one of possible ways to parameterize this function. And a priori, we don't know if it is good choice or not. This is just some choice. Let us look what it will lead us. So we need to calculate again the partition function, this one. Their summation goes over all configuration of sigma with subscripts A and B belongs to this replica space. Now, the sum over all these replicas can be rewritten in the way which you see on the upper line. It is just rewriting of this sum. What you see here is just some algebraic equation. And we need to, in order to calculate it, this trace over all sigma, A. As before, we need to decouple different replicas, which is done again by introducing some arbitrary fields. When it was replica symmetric solution, we had just a single random field Z. Now we have many of them in order to reproduce the expression above. So there is Gaussian field Z with variance Q naught, and there is some number of additional random fields Y. The number of this is a number of blocks, which you see here. You see that all the size of matrix is n, size of block is m, so there is n over m of these blocks. And for each of these blocks, we should introduce a Gaussian field. Here, after we rewrite it via this set of Gaussian integrations, now each sigma is independent of other ones, like it is shown here. And we can make a summation. Summation leads to this result. You see, there is each sum of the sigma gives some hyperbolic cosine in a full effective field, which is a sum of Z and Y. Now, variance of this Y field is Q1 minus Q0. And here we have this. Let me mention, just emphasize that what you see here is a power m, and then the whole this expression in square brackets should be taken into a power n over m. Okay, up to now it is just algebra. And this way we find a free energy, which is a function of Q matrix, and Q matrix is characterized now by three variables, Q0, Q1, and M. Now there is a, a tricky point. We know that yes, we need to take a limit n to 0. And originally n was integer and m was also integer and less than n. So how to understand this limit? We start from this interval for m, but we need to put n to 0. The result is that we can take limit n to 0, and then m will be defined on the interval from 0 to 1. This is not at all obvious, but for now we will just take it as it is, and then later on I will demonstrate you arguments why it should be why we should indeed consider m in this interval between 0 and 1. Note that here, when m is uh, between 0 and 1 and n sent to 0, coefficients in both these terms are negative. And the whole free energy as function of free parameters is given by such an expression. Also, we can note that if we put m equal to 0 or m equal to 1, we will be back to the original replica symmetric solution with parameter q equal to q naught or q1. As we already discussed a few times before, the specific feature of spin glass theory is that instead of looking for minimum of free energy, here we're interested in the maximum. In as I mentioned previously, we have here a quadratic form which has, for m between 0 and 1, it has explicitly sign minus here, which corresponds to the maximum. Good. Now, in general, we can write down equations for extremum of this function over all three variables. And for arbitrary beta inverse temperature, these equations cannot be solved analytically, but they can be solved numerically. What are properties of these solutions in our pairwise spin glass model? Indeed, we will find a solution with parameter m between 0 and 1. The actual value of this m depends on temperature. And it depends on such a way that both, by the way, here 1 is just DC in the normalization for coupling, which I used, J equal 1. So the solution starts from m equal 0 at critical temperature, and in the limit of 0 temperature, again, it goes to 1. Let me mention already at this point that the fact that m starts from 0 at the critical point is a specific feature of Sherrington-Kirkpatrick model. And for other types of spin glass models, which I will discuss today later, it is not the case. In that cases, it starts not from 0, but from something close to 1. Now, with the solution, we have one-step replica symmetry breaking. Again, we can calculate entropy in the limit of 0 temperature. It is still negative. But the numerical value of this negative entropy is much smaller. It is like minus 10 to minus 2. So the conclusion is that it is not still good solution, but we make some reasonable step. Finally, as I mentioned on previous lecture, the replica symmetric solution is, we can see that it is not correct, not only because of negative entropy at low temperature, but also because it is unstable with respect to Gaussian fluctuations. Here, it is again unstable in the same sense, but similar to the entropy, just numerically, the magnitude of this negative eigenvalue is order of magnitude smaller. Good. How to advance? That was proposed by Parisi again, and the way to advance is to continue to divide our matrix over blocks in the way which you can see here. Now, instead of single special diagonal, we have these blocks, the same blocks with the parameter Q1, but inside each block we select some other set of blocks with which are even closer to diagonal with order parameter Q2 in exactly the same way. And when we repeat this procedure more and more to have a whole sequence of parameters with mi, repeating the same hierarchical construction further and further. On a schematically, it can be shown by such a tree diagram. So replica symmetry, no replica symmetry breaking, we are all here. First replica symmetry breaking, we have number of branches with Q1. Then we split each branch further. And we repeat it basically to infinity. It means that when we have some like k level of replica symmetry breaking, there are these k plus 1 parameters. All of them are between 0 and 1, but eventually it will become a continuous function. Instead of some large number of discrete variables m, we will come to the functional order parameter, which you will see soon. Yes?
So how to decide how many branches we have from Q1 to Q2?
Well, here it is just the number of these large blocks.
Okay.
But when it becomes some continuous number. So it is only qualitative, representation. It does, yes, this number does not have any real physical signature. It just tells you that you need to split the initial state to some number of other states. It is not intuitive at all, I should admit. But this strange mathematical construction has some relation to physical reality, as we will see a little bit later. So when you make this k-step replica symmetry breaking, you get some complicated expression. And the goal is to come eventually to parametrization in terms of continuous function. How to do it? That was found. I will not try to explain how they did it. It is a long story. But there are these two papers mentioned here, where they derived the expression of the free energy in terms of continuous function q of x, where x goes from 0 to 1. Now, what is here? Simple integral over q when there is some action which is functional of q of x. This functional is a Gaussian integral over z, which can be considered as some random frozen field. And here it is a function j. J is a function of two arguments in general. It is a function of x. It is the same x which goes here. And it is a function of effective field z plus h. H is an external magnetic field. It might be 0, for example, if there is no external field. Z is a random field with variance q of 1. And function j should be obtained from such a nonlinear equation in two variables. Boundary condition for this function is this. So this is, you see that it is just a free energy for a spin which sits in a specific field y. But here it is boundary condition in the sense that j is taken here at x equal 1. But what we need to find in order to calculate the action is this function at the argument 0. So in order to come from this trivial dependence to what we need, we should solve this nonlinear partial differential equation, which is possible numerically. Now, here it is still not the whole. What is written here, it is not sufficient, because this equation for j depends on q of x, and we need to find what is q of x also. In order to find this q of x, we need to look for extremum with respect of this free energy f, extremum over functions q of x. This saddle point equation is equivalent to the following equation. Q is the integral of m squared. M, as you can guess, is a local magnetization in the presence of field Y. And the equation for this M is written here. It comes when you make a variational derivative of the functional f. This equation again has a boundary condition. Simple interpretation is that when you see here 1, which means this q equal 1, it corresponds to the magnetization within just magnetization which is in the for spin in effective field Y. And here what is described by this boundary, here you still do not account for multiple solutions of these equations. If you will think for a moment in terms of, say, Thouless-Anderson-Palmer equations written without averaging of a disorder, then, as we discussed, these equations, they have explicit physical meaning, but the solutions of these equations is not unique. There are many solutions, and even many solutions which are local minima. So, qualitatively speaking, in order to account for this multiplicity of solutions, we need to start from this trivial equation, but then to come to the corresponding function at smaller q or a smaller x, eventually moving to this x equals 0. So we have two functional equations. One is this, another which I have shown here for J, and these two equations should be solved simultaneously, and in order to find function q of x. And its inverse function s of q, which, as we will see soon, has even more straightforward interpretation. But before, let us consider a very much simplified example. These complicated nonlinear functional equations are needed to describe the system at arbitrary temperature. Close to transition temperature, we can do these things much simpler. Namely, close to Tc, we can use expansion in power of these matrix elements, Q, A, B. As you remember, for replica symmetric solution, we have just one number, Q, which was proportional to this small tau, close to Tc. The same will be true for other matrix elements. So expansion up to the fourth order in Q matrix elements looks like this. And the key point, the term we need to consider is this one. It is exactly this term with this negative coefficient, which was responsible for instability of a trivial replica symmetric solution. Okay, now let us rewrite this free energy in terms of function q of x. The function contains this sum of the replica indices, couple of terms with trace, and this 4th order term. So the rule is like this. We recall the discrete parameterization of the matrix and rewrite any power of matrix elements which we need here in such a way. Here, when we see this mi minus mi plus 1 in discrete version, it becomes an integration element dx after mapping to continuous function. Of course, we will understand that it is impossible to understand details of this construction just from the presentation. So my goal is to give you some general idea what happens. And in order to learn it seriously, you need just to study these papers. There is no other way. So in terms of continuous function, free energy looks like this. And we need to take a variational derivative over q of x. And we come to such equation. The same equation is rewritten here. Now let's solve it. It is not so, this equation is not so difficult to solve. First, we simply take a derivative over x. As a result, we will see this equation. And because it is a product, either one multiplier or another should be 0. So either expression in brackets is 0 when we have this equation, or q of x is 0. Of course, if this q prime of x, derivative of q over x, of course, if it would be 0 for all values of x, then we would be back to incorrect replica symmetric solution. But this q prime can be equal to 0 on some intervals of this interval, on some part of the interval between 0 and 1. In particular, we can look for the solution of this equation in such a way that between 0 and some x naught, it is q naught so q0, then it goes linearly, x naught, some x1, and then again it goes as a constant. Such a solution it is just easy to check that this kind of solution will solve the equation here. It will contain some terms, linear and quadratic, and they will all cancel each other. But we still have parameters Q0, Q1, and X0, X1.
Is this the only one solution? Because it seems that we can put a couple of more regions with that Q of X dependence just in between X1, X2, X3, which here is between X0 and X1. So we'll have like ladder type of the solution. Or
you can do it, but then you will need to find the magnitudes of all these parameters. Like here, for example, this is not solution; it is ansatz, which contains some numbers which are still arbitrary. Now let's find this, and then let's find what comes from here, and then we can try to generalize. So we substitute solution with these parameters into original equations at the points x0, x0, and x1. These these equations are written for the case of zero external field, by the way. In principle, what do I have here? Yeah, it was zero everywhere here. I mean, in general, I could write down the same kind of equations with non-zero external field. But the effect of this field we will discuss later. Now this field is absent. And after substitution of this piecewise linear solution, we come to this couple of equations. Solution of these equations is that Q0 is 0 and Q1 is approximately tau. As a result, the whole function looks like this. And x1 is related to Q1 as was already shown here. So x1 is 2Q1, so it is 2 tau. So even close to transition temperature, we find this non-trivial function Q of x, not very complicated, just piecewise linear, but still some function. Now, what happens in higher order? This is solution valid in lowest order in T minus Tc. It can be extended to higher orders of Tc. For example, in this paper of Zomers, it was found up to tau in 5th power in T minus Tc. And the solution which he found is linear term with some coefficient depending on tau, then some cubic term, and constant beyond some breakpoint x1. Now, what about stability? First of all, we can easily check that this solution in the order we found it exactly fulfills marginal stability condition we learned from Thouless-Anderson-Palmer approach. Then let us discuss stability in terms of this replica symmetry breaking directly. That for general arbitrary temperature, I don't know if it was done. Well, it was not done long ago, but maybe it was done later, that I don't know. But in leading code approximation in tau, we can, because we have explicit expression for free energy in terms of Q matrix, we can find the Hessian, so the second derivative of the free energy of the matrix elements. It is this K matrix of rank 4. So here in this matrix, we need to substitute the solution. And then to consider some small variation of Q of x close to this piecewise solution which we found. So we write it down like this. Q is Q with subscript C is our solution for extremal, and plus some small variation Qt. This is equation on the top is quadratic in terms of Q tilde. So we need to take to look for eigen functions of this equation, which leads to again a linear equation for Q tilde. And we can check that all eigenvalues are negative. So there is, which corresponds to stability in terms of this replica theory. Now, what happens if there is a magnetic field, non-zero magnetic field? If it is small and magnetic field and we are still not far from transition temperature, then solution which we discussed generalizes to this one. Again, it will be constant at some interval of x, linear piece, and the difference is that this Q naught will be non-zero. Q naught will be given by this expression. It is also possible to find the shape of Q of x function in very strong field. As we discussed it some moment previously, even at very strong magnetic field, still there is some low positive temperature such that a trivial replica symmetric state will be unstable. It is the Almeida-Thouless line. So what happens below this line? The solution can be found. I will not describe it now, but it is of such a form. There is no linear piece here. It corresponds just to two different constants. So in a sense, it is basically a one-step replica symmetry breaking solution, which in the limit of very strong field, it is okay. So it is again the same, just reminder of the same results, that for strong field, this instability temperature is exponentially small, but still non-zero. Good. Now, what are physical consequences? The field-cooled susceptibility, so we put some magnetic field and cool. Then we find a magnetization which is proportional to this external field. I mean here weak magnetic field. And coefficient of proportionality will be this expression where now what is this Q? It is a here this Q Edwards Anderson, which as I put it, it is in replica language. It corresponds to such expression where you see there is Q1 and 2 are two different replicas. Of course, when we use replica symmetry breaking, we need to consider symmetrized expression. So it was, you can derive expression for this Q introducing two different replicas, but then you need to make symmetrization. So instead of this expression, you will come to such a sum of all Q alpha beta divided by n. Then when you translate it to continuous language of continuous order parameter, it becomes such a integral Q of x over all x. Let me remind you that zero field cool susceptibility here is equal to 1 over t 1 minus q of 1. So the difference is that here it is only q of x equal 1 enters, while here we have an integral. And because q is not constant, these two things are different. Interpretation. Q of 1 measures correlations between spins within any specific local minima. We know there are many solutions of extremal equations for local magnetization. If we are sitting in a one of these local minima and apply weak magnetic field, then what we measure is this. Now, with field-cooled magnetization, the story is crucially different. We start from applying magnetic field and then we cool. It means that depending on the value of this magnetic field which we used, the system will choose some different metastable states during its cooling. So the presence of many possible metastable states will affect the final result. In zero field cooled experiment, we know only about the properties of some single minima, and we don't know anything about other. In field cooled, we know that there are many of solutions, and during cooling, the system chooses some most appropriate one. So the differences shown here. This broken line is a zero field cool susceptibility, which goes to zero linearly when temperature goes to zero. While equilibrium zero field cool response is just a constant. Below transition temperature, it does not change. Field cooled. Yeah, it is in some sense equilibrium, yes. Here, with equilibrium states instead of field cooling.
It doesn't depend on the value of the field.
But this is linear susceptibility.
Yes.
It is in a weak field limit. Now,
The cooling procedure must be adiabatic, or can be also something step.
It is assumed to be slow, but of course, the question what it means quantitatively. For infinite range model, you have some spectrum of relaxation times, which is a power law spectrum. So basically with spectral density, which behaves as square root of omega. So, and then you have some, roughly speaking, infinite times. If your system is large, then all relaxation times which are needed to pass from one metastable to another are exponential in size of the system. So there is a big gap between microscopic and macroscopic times. In real spin glasses, it is not so simple. The spectrum of relaxation rates is actually continuous. And this is why in real spin glasses, as I mentioned, I think in first lecture, in real spin glasses, response depends not only on trajectory in the phase space, so a space of parameters. So not only field-cooled magnetization is different from zero field-cooled one, but also it may depend on how fast you cool the system. And this phenomenon is called aging. Now let us discuss overlaps between different metastable states. This, if we have two different states, alpha and beta, in each of these states there is some set of local magnetizations, Mi. Then you can define overlap, just this. And correspondingly distance between two states. It is just Hamming distance, how roughly. M is not binary, it is continuous thing, but at least in zero temperature limit, it would be just Hamming distance and nothing else.
Sorry. Just to make sure. So each metastate
No, it's more tricky. Q of x with Q of x is does not describe a specific metastable state. It describes ensemble. It describes statistics of all these states. As you will see, it describes actually the probability distribution to find some specific value of overlap. So this is overlap. Now, there is a probability to find some value Q for overlap. This probability is given by a sum over all possible states, alpha and beta, with W alpha, W beta probability that the system is staying in the state alpha or beta.
So you defined earlier the W to be the weight given by the exponential minus the free energy. And the free energy is determined by the local magnetization and also Q or not. Those three So f of alpha is determined, if I know all the local magnetization inside a pure state.
Yes.
Determine f of alpha or not?
Yes, yes.
Okay.
Yes,
So
yes.
each pure state is determined by the local magnetization.
Yes. The point is that there are many states, alpha and beta, with energies which are not much different between them. So the barriers between them are thermodynamically large, but the values of free energy not necessarily so large. So this is why when you take this statistical average, you need to account for possibility to be in different configurations.
And the barrier is very large because I needed to do a non-local excitation to go from one to
Yes,
the other.
yes. Okay, so here what is written is the expression for this this Q with subscript 1 or a 2 or a K is just a correlation function made out of K spins. In particular, for Q1, it is with subscript J, by the way, means that it is calculated for specific realization of this set of random coupling J. And then, of course, we need to average over it, so, which is shown here. This correlation function is an integral over Q with probability distribution at a given J, P of Q with Q in some function. Good. And to derive this equation, we used this the fact that connected correlation functions vanishes inside each individual state. Now let me come back and present you some arguments why M should be between 0 and 1. Here I follow the exposition in one of the books mentioned in the beginning. It is book of the Dominicis and Giardina. This is overlap distribution function. Now, for replica symmetric solution, it is trivial. It is just delta function with some q. One step replica symmetry breaking. It is the sum of terms. What are these terms? One is that q delta function of q minus q1. Another is that it is q minus q0. It is a probability distribution, so it should be positive. And the coefficients here in the limit of n going to 0 becomes this. So from the condition that probability distribution is positive, we conclude that this should be positive and this should be positive. So m is between 0 and 1. Also, let me mention that what is the meaning of this one-step replica symmetry breaking. It means that overlap between any two states could be equal either to Q0 or to Q1. Largest of them, it is Q1, is just self-overlap. Self-overlap is the same as sum over n, 1 over n, m, I squared, where mi is sigma I average. So this is the same as original Edwards-Anderson autoparameter. Now, in the absence of magnetic field, we have seen that Q naught is equal to 0. So probability distribution tells us that either we have self-overlap or here we have 0. So overlap between different metastable states is 0. They are not correlated. This is what we learned from one-step replica symmetry breaking. There are the statement is there are many states, and different states do not correlate. When we come to say to the continuous replica symmetry breaking, it tells us that there are many states and there are some correlations between them. So Q, this Q correlation function in power k is the integral with distribution P of k. Here we already, so we can express it in terms of this sum over replicas with q in power k. Sum over, which we need here, let me remind you, is this integral. So by comparison between this expression and this one, we conclude that P of q is nothing but derivative of inverse function, S of q over q. And as a result, this solution for close to transition temperature gives us P of Q, which is some constant when Q is less than Q1, plus delta function. This is self-overlap. And here it is shown, well, it is not constant because here this plot is done not for lowest order in T minus Tc, but including next orders. So as you remember, this function Q of x is then not just exactly linear, but contains some third order correction. So it is a piece of continuous function and a delta function at the edge. Good. Now another very important point. Let us consider overlaps between three different states. 1, 2, 3. Pairwise overlaps. It is defined like it is shown here in this formula. Using this Parisian ansatz with continuous solution for Q of x, we can show that three numbers, you see, when you have three states, there are three distances. It is like triangle. There are distances are defined like this. Distance between A and B is self-overlap minus overlap. So the simplest statement is that among that all these triangles, if we imagine a triangle and free distance between 3 points, all these triangles have at least 2 equal sides. There are no triangles with 3 different distances. It is not Euclidean matrix, it is what is called ultrametricity. Why it is so? To understand it qualitatively, let us consider such a tree diagram. Suppose that we consider 3 states, one corresponds to this point, another to this point, and the third one somewhere here. Distance between these 2 points is measured by 1 step up. In order to come from this state to this, we need to go 1 step up and then back. In order to come from here to here, we need to have 2 steps up and back. The same for this and this state. So the distance between this and this is the same as between this and that. And this relation between overlaps is just this mathematical consequence of the solution in terms of continuous function Q of x. If it would be one-step replica symmetry breaking, then there is no such equation because here just all overlaps between different states are simply zero.
Ultrametricity, like the distance between points at the same level. Or we can take
Yes, we consider distance on the same level, of course. Yes.
Practically, one numerical can check if there are different D.
Yes.
Then it infer that there is a two or three step symmetry.
Yes. It is possible to check numerically with the statistics of overlaps. Yes, and to check that indeed it has this ultrametricity property.
And all the DAP, all the different different values must be different to have multimetricity.
Ultrametricity. So say it again. They should be different. In what sense?
How to define numerically if there is or not ultrametricity?
We find many magnetization patterns and then calculate overlaps and just calculate this distribution function like it was like it is defined here. Of course, you need to make some smearing of delta functions, but in principle it is straightforward.
So maybe a little bit of question about multimetricity, how before we went far. Two main problems which we faced when we used one-step symmetry breaking was the instability to those operations and entropy. Do we also calculate those in this case of having a hierarchy and it's continuous?
Yes. A continuous solution leads. First of all, it is marginally stable, as I explained. And second, you can solve this awful set of nonlinear equations in t to 0 limit and find that entropy goes to 0. So, major points of all this. First, that indeed there is a reasonable solution in terms of this continuous Parisian ansatz, which has no bad properties. Entropy is always positive and goes to 0 at t to 0. It is marginally stable. Second, this solution corresponds to a large number of pure states with some overlap statistics. This solution refers to specifically to Sherrington-Kirkpatrick model. And on the next lecture after lunch, I will tell you about a few other models where continuous replica symmetry breaking is not needed. And one-step breaking is sufficient. Now, the major question. It is a good theory for infinite range model. Is it good for real spin glasses? On purely theoretical level, nobody knows. because there is no theory for real spin glasses below transition temperature. It was a big discussion during like 10 or 15 years long ago between two groups who advocated for absolutely opposite view on this issue. Namely, groups basically in Italy and in France, mainly in Italy and France, were in favor that this Parisi scheme is qualitatively good for real spin glasses as well. Although, of course, everybody understands that it cannot be exactly correct. The point is that in real spin glasses you have some finite range of interaction, first of all. And it is difficult to imagine that some regions of this spin glass, which are very far apart one from another, could belong to just the same pure state. But the point was that still qualitatively, and first of all in the sense of a presence of some hierarchical organization of these metastable states, it should work for real spin glasses as well. Contradictory point of view was developed in US. Mainly it was a very influential paper of David Hughes, Daniel Fisher, and Matthew Fisher, who advocated a simple, if not trivial, picture. They were saying, well, you know, spin glass, it is just a collection of some long, slow excitations, like you have some where a piece of this spin glass, they call it droplet. Then this droplet can flip somewhere. It will cost some finite, although large energy. And then, because the energy is large, the corresponding time scale will be very slow. And with some appropriate distribution of these rates or sizes of droplets, there are many parameters, you can play with them. And with this kind of model, we can explain everything what is observed in this spin glass state. Discussion was long because simple correlation functions, like two-spin correlation functions, they cannot distinguish between these two pictures. You always can choose one model or another model, fit some parameters, and both will be okay. Very important experimental contribution to this discussion was made by the group of Mike Weissman in Urbana. What I present here, it is a reference to his review article, but the real research article which they published with Israelov and others is, I think, something like 50 or 60 pages in journal. It is a detailed description of a very interesting experiment. We studied metallic spin glass, copper manganese, I think, and some small piece of this spin glass. And what we measure was noise in electric conductivity. So we measure conductivity in low temperature phase of this spin glass. They detect fluctuations of this conductivity. Then they relate this fluctuation of conductivity to fluctuations of magnetization. Now, the simplest just usual noise of this magnetization. As I already explained, it is not very useful because it cannot distinguish between two basic theoretical approaches. So what we measure was a noise of the noise. You measure noise in some broad interval of frequencies. But so what you find is a spectrum, spectral function of this is a frequency. But when you measure it long time, and you see that, of course, you can. This function itself is not also. It is not just some. When you measure it in different during different intervals, you find something different. So this thing itself also fluctuates. And what we extracted was fluctuation of noise, which is equivalent to the measurement of sigma t, sigma t1, sigma t2, sigma t3, sigma t4. So what we effectively measured is 4 spin correlation functions. And these 4 spin correlation functions indeed can distinguish between parallel dynamics of droplets and hierarchical dynamics. The crucial point is that in parallel dynamics, by definition, what you have is a sum over some independent entities. The distribution of rates, for example, you could choose as you wish, but still it will be, you will have some, how to say, large, by the large number theorem limit, you will see that this noise is some stationary thing. You can do it whatever you can put it by any form in terms of this S of M, but it will be some stationary function. While in hierarchical picture, large degrees of freedom, large, I mean in terms of large variation of magnetization or a large energy barrier, they are composed of smaller ones. So they are not independent. And therefore, second noise is much less trivial. Conclusion of this really beautiful experiment was that they say we see hierarchical dynamics, not a parallel. I would like to see now even a single group able to do experiment like that. I mean, that was done really, it was a really very complicated and very long experiment. We're willing to find an answer. And as Weissman wrote in this rather short review, originally he wrote, I thought I will find parallel dynamics. But we tried, we measure, and we find no. Parallel dynamics does not account for our result. Good. So that's it for now.
The difference between these two approaches will be also if the order parameter that you drop it, usually it would be not a continuous.
They just we don't discuss all the parameters at all. It was simply, how to say, it was just phenomenological description. We know that there is a slow dynamics. How can we describe it? So let's assume we have some, that in the size of L, we have L to some power, not necessarily dimension of space, maybe less, some number of spins which can flip together. And we will have some energy barrier, also some power. So that was not it was nothing than just phenomenological description, but rather elaborated. Okay, so lunch break.